Alright, we're going to be looking at 11.6 together. Nice to have you with me, and I hope that you're doing well. So make sure that you write in, of course, the essential question: how do I find volumes of prisms and cylinders? And if you would also have out your Chapter 11 volume and surface area formula sheet, especially this area is what we're going to be looking at. And so this section, 11.6, is looking at volumes of prisms and cylinders. So just focus on those two words, prism and cylinder, and contrast that with pyramids and cones. Our next section, 11.7, is going to be looking at volumes of pyramids and cones. So what is it that is alike between prisms and cylinders, that in contrast to pyramids and cones? And the answer is that prisms and cylinders have two bases. That's why for surface area over here we're going to do two bases, and for pyramids and cones they just have one base. Okay, so therefore we can use this equation for volume for both prism and cylinder. Base, that is the area of the base, times the height. Whereas when we do our next section for pyramids and cones, it's going to be 1/3 the area of the base times the height. So here in your notes, they explain to us that the volume of a solid is the number of cubic units contained in its interior. So here's a solid, and the volume is the number of cubic units contained in its interior. The volume is measured in cubic units, such as cubic centimeters. So for example, here's a cube, meaning that each of these sides, the base and the width and also the height, are all the same dimension, same length. And so the volume of that cube is the length of the side cubed, or raised. That's an exponent, so it's raised to the third power, which of course you understand is s times s times s. So we're accustomed to s squared, which would be just s times s, but here it's s cubed raised to the third power. And so that is, you have three of the bases multiplied times each other, s times s times s. I say base meaning the term base in contrast to exponent. So for example, if we had a cube that the side length was 2 centimeters, then the volume would be 8 centimeters cubed, because it's 2 times 2 times 2, which gives you 8. 2 times 2 is 4. 4 times 2 is 8. So that gives you a sense of how quickly that volume increases as you increase the length of the side of a cube. They also give us some theorems here in the book. The volume of a cube is the cube of the length of its sides. That's what we just looked at. So you just take the length of the side and cube it. Volume congruence postulate. If two polyhedra, remember polyhedron is the singular term. It's a solid contained by polygons. Polyhedra is plural. So if two polyhedra are congruent, then they have the same volume. If they're congruent, if it's the same shape and same size, then they have the same volume. The converse of that is not true. If you were to switch these, you could not say if it has the same volume, then they're congruent. But it is true that if they are congruent, then they will have the same volume. And then volume addition postulate, that the volume of a bigger solid is the sum of the volumes of all of its non-overlapping parts. In other words, what they're saying is we can take some big, funky, irregular is the term, irregular solid like this, and we can break it up into smaller solids that are regular, in the sense of that we are able to figure out, not regular, that's more of a technical term, isn't it? But we are able to figure out or in geometry it is, the volume of this solid. So that's number 1. And then here's this long one, we'll call it number 2, and number 3. So the volume of the total of this is volume 1 plus the volume 2 plus the volume of 3. So let's look at 1 here. And, well, first let me look at the big picture. These dash lines, whenever you have dash lines like this, it almost always means that these are surfaces of the solid that you would not be able to see when it is a solid. So those would be hidden, those are behind what you can see out in front here. And so what I typically like to do is to draw in these, and actually this is already drawn in here. Yeah, in this one it is drawn in. And so you can see out in front here, let's just count up the number of blocks. So here's 1, 2, 3, 4, 5, 6, 7. So this front surface area is 7 blocks, so 7 units. On the left hand side up here, this is 2 units. So let's try to figure out just this block number 1 up on top here, or shape number 1. And since I had 1 and 2 blocks here, it's the same length across here, so it's 2 blocks going across the front, and then it's 2 blocks going back, and then it's 1 block going up. So we can say that the base times the width times the height, our base is 2, our width is 2, and our height is 2. Right? Because this is a prism, this little guy up on top here. So volume equals base times width times height. And like I said, the base, we can think of it as 2, the width as 2, and the height as 2. So 2 times 2 is 4, 4 times 1 is 4. First time I did this, I put 5 here. And I had everything else right, but my answer was 21 because I did not multiply it correctly. So just another example that I make mistakes, and I need to go back and double check my work, and so you are probably like me, so make sure that you double check your work. So this shape up here, solid 1, is the volume of 4. Let's figure out the volume of this long one here, and so this was 7 and 2, and then my height is 1. I just have a height of 1 on this solid number 2. So that's a volume of 14. 7 times 2 times 1 is 14, if I have it correct. And then my third solid up here is 1 times 2 times 1. So 1 times 2 times 1 is 2. So my volume for this entire irregular shape is the sum of the individual volumes. So 4 plus 14 plus 2 is 20. So break irregular shapes up into, I don't want to say regular, because remember we say regular means equilateral and equiangular, so I would say more normal shapes, or standard. There's a good word, standard. Break it up into standard shapes. Next page on your book, I have that here in your notes. Let me position this correctly for you here. So this guy is a prism. Has 2 bases, so you could actually put a big capital B up here. Go ahead and do that. Put a big capital B. So it's a prism. It has 2 bases, and the volume, therefore, looking back at your reference sheet, the volume for a prism and also a cylinder is the area of the base times the height. Area of the base times the height. So the big, large, or capital letter B is the area of the base. So the volume of this prism is the area of the base times the height. And what kind of shape is the area of the base? It is a rectangle. So put an arrow up there saying that the area of the base is base. That's lowercase base. You might think of it as, if you want to label that, this distance here is lowercase base. We'll just refer to that as base. Whereas when we have the capital B, we will refer to that as the area of the base. So the base is this length here, and the width is this length. So the area of the base, capital B, is base times width. And you see that also in your reference sheet in a parallelogram, where you can say that, remember, rectangle is a type of parallelogram. A parallelogram, the area is base times height. Move this light over here so it's not making as much of a shadow to the side. Alright, so the area of a prism is just the area of the base times the height. Similar concept for the area, or the volume of a cylinder. The volume of a cylinder is the area of the base. This times, in this case, what is the shape of the base? The base is a circle, and going back to your formula sheet, you will remember that the area of a circle is pi r squared. So that's why they have here that the area of the base is pi r squared. So therefore, since this is a cylinder, we can use the formula V equals area of the base times the height, and the area of the base is pi r squared. So if you would put parentheses around the pi r squared, maybe an arrow, so remind you that the area of the base is pi r squared, and then multiply that times h. I tried to put the h there to the right, and it looks sloppy, doesn't it? But just so you understand, it's not just pi r squared h, it's pi r squared, that's the area of the base, times h. So it makes more sense to you, and so that way it'll be easier for you to remember that formula. Because remember, none of these formulas, the only formulas that you're going to have on the FSA reference sheet is volume equals area of the base times height, volume equals 1/3 area of the base times height, and the sphere volume equals 4/3 pi r cubed. Those are the only three formulas from this chapter that you're going to have. Alright, let's do an example. Let's get rolling here. Example number 2, I've kind of laid down the foundation, so now we can get a little bit quicker here. So what kind of shape is this? This is a prism. And what is the shape of the base? The base is a trapezoid. So back to your formula sheet, a trapezoid, and if you would, go ahead and draw in this shape for a trapezoid to remind yourself that a trapezoid has two bases. You'll remember also that each of these bases are parallel to each other. That's what makes it a trapezoid. So the area of a trapezoid is it's like a triangle, but it's 1/2 height, and since you have two bases, you add those two bases. Maybe I'll emphasize there are parentheses around these two bases, and you are adding them together. So that's the area of the base. So where are we at in the book here? So to find the area of this trapezoidal prism, remember you describe what kind of a prism it is based on its base, determined by the shape of its base. So it's a trapezoidal prism. And the area of a trapezoid is 1/2 base 1 plus base 2 times the height. So this length, this larger base is 14, the smaller base is 6, and the height of this trapezoid is 3. So that's where they get those numbers here, and multiplying that together you get 30 centimeters squared. So the area of the base is 30 centimeters squared. The area of this base also is 30 centimeters squared, and you multiply it times the height, which is 5. And notice here I put this h is the height of the trapezoid, whereas this h here in the book is the height of the solid. So when they say height, got to be careful. Are they talking about the height of the base, which in this case is a trapezoid, or are they talking about the height of the solid, the entire solid? So the area of the base times the height of the solid is 30 times 5, which is 150 centimeters cubed. Let's look now at a cylinder. These are easier. What is the shape of our base? And it is a circle. Okay, what is the area of a circle? Equation for the area of a circle. And you'll remember that it's pi r squared. You also have that here in your formula sheet. Here it is. The area of a circle is pi r squared. So we take our, did I say pi r squared? Yeah. So what's that? Oh yeah, okay, here. They didn't put it in here. They calculated up on top here. So pi r squared, our radius is 9. So that's where they get the pi r squared, pi 9 squared is. And 9 squared is 81, so 81 pi. And that is your exact answer, 81 pi. Let's plug that in now to our formula here. Volume equals the area of the base times the height. Area of the base is 81 pi. The height of our solid is 6. You see here it says 6. So 81 pi times 6. You multiply the 81 times the 6, and you get 486. So 486 pi is our exact number. And then plugging that into your calculator and round it to the nearest hundredth, you would get this number here. One more example before we cut you guys loose to do some problems on your own. If they give you the volume, there's a cute little clock, and if they give you the volume is 90 cubic inches, then you can find the length of this cube. Cube again meaning the base and the width and the height are all the same measurement. You can find the length of the side by plugging it into your formula for the volume of a cube. And so now I have 90 equals x cubed, or you could say x to the third power. So how do I get rid of the third power here? Well, I do that by taking the cube root. So we're accustomed to the square root, and we'll talk more about this in class. Square root has an invisible 2 here. Cube root has a 3, so you actually write in a 3 into the little root there. So this is a cubed root. The root is a power of 3. In other words, you're looking for a number that you multiply that number times itself 3 times. So remember, 2 cubed is 2 times 2 times 2, which is 8. So the cube root of 8 is 2. And on your calculator, you would, let's first turn this beauty on. Here we go. Make sure you can see it. So the on the calculator, yours is a little bit different, but it has a similar button. And this you can see the x to the root. And so in this case, what we want to do is say 3, and then second, and then hit that button. So you see on mine it shows the display of the root, and then in this case we want 90. So you want the cube root of 90, which is 4.48 rounded like they have here. So again, you're using this button here, the root with the x in it, and first you put the number of the root, and then you hit that button, the second in the button, and then you put the number that you want to take the cube root of. And we'll practice that in class. Okay, it's your turn now. This guided practice, and let me help you out. So don't turn off the video yet. Let me help you out. So number 1 here, in order to find the volume of this shape, this is an irregular shape, so let's turn it into some basic shapes. And so first of all, let's draw these little guidelines on yours. So they're telling us that this distance here is 3 units long, and I can see that now. So let me draw these guidelines in here. So 1, 2, 3, and this distance to the left is 3 units. So let's draw those guidelines going across. So I have 1, 2, 3 blocks there. A little more difficult are these diagonal guidelines, but follow the pattern of the far left here. See how this is kind of diagonal going off here, and this one also is diagonal. So the division between these two blocks will also be diagonal, and then same thing over here on the right side. Follow, make sure that your guideline is parallel to these other ones that are edges that are drawn here. So now it's easier to see. Okay, so I can get the volume of this guy here first, and then get the volume of this larger one. So break these two volumes, this larger volume, into 2 different shapes, and write this out. Don't just give me a number here. I know it's easy to count now, but write in here volume total equals, and then label this as solid 1, and this is solid 2. So volume total equals solid 1, volume of 1 plus volume 2, and then tell me what 1 is, tell me what 2 is, and then add them together. Okay, do that so that you can make sure that you double check your work and get it right, and also so that you can come back later and remember how to do this. Number 2, they're asking for find the volume of a square prism. So it's a square prism that has a base edge length of 5. So remember, this term is actually an adjective. It's not a noun. It's an adjective that's modifying prism. What kind of prism is it? It's a square prism. So the shape of the base is a square, and the length of each side is 5, and then the height of this prism is 12. When I first drew this, I picked up on the word square and I drew a cube. And then as I tried to label it, I was like, wait a second, that's not going to work. So I got that wrong because I went too quick and just saw the word square and thought it was a cube. But no, it's a prism whose base is a square, but the height is much longer than the base. So it looks like this. So go ahead and write out your formula, and I'll solve the volume for that one. And also draw the picture for this right cylinder. The way I do it is draw a circle up on top, and then draw my parallel lines, and then an arc, and then try to fill in the circle. It's not very good, is it? I could draw a lot better. You could draw a lot better, I'm sure. So draw a circle, and then complete the rest of the circle. Actually, you know what? It's not a circle, is it? It's an oval, because you're looking at it at a slant. So maybe what I had there was actually pretty good. So it's not a circle, it's an oval, because you're looking at it from an angle. But fill this in, and it's dashed in the back. So that's your right cylinder. Okay, go ahead and pause the video and do those 3, please. Now in your book, Cavalieri's, there's this dude named Cavalieri, Bonaventura. That's interesting. His first name ends with an A, but it's a dude. Maybe it's a girl. Wouldn't that be cool if it was a female? That'd be nice. Anyway, this person, Cavalieri, in the 1600s, discovered this principle that if 3 shapes have the same cross-sectional volume, cross-sectional area. So these 3 areas are the same, and if they have the same height, then each of these volumes, the volumes of each of these solids, will be the same. So in other words, you can take a prism, a right prism. Remember, right means it has a right angle here, and then squish it over to the side, and it's still going to have the same volume. Let me show you that with my pennies here. So I have 5 pennies, And if they were to be a right, so we can do this in a way that the shadows don't make it look, you can see it more clearly. So if I have a right, in this case it would be a right cylinder, and it was 5 tall, 5 units tall. It's going, and let's say that each penny, the area of the base here is 1, and it's 5 tall. So therefore, the volume of this right cylinder is going to be the area of the base, which is 1 times the height, which is 5. So therefore, this is 5 cubic units, whatever the units are. Now, if I was to slide this thing over to the side, so it's no longer a right right cylinder, it's still going to be the same volume. As you can see, I've not changed the volume of each of these 5, and as long as the cross section of the shape, it remains the same, and the height of the shape remains the same, the volume will be the same between those. So that makes it then easier to find the volume of a slanted cylinder like this. As long as the two bases are congruent and parallel, they have to be parallel, then we're fine. So we just use volume equals the area of the base times the height. The area of the base is pi r squared because it's a circle, and their height here is 7. So find the area of this base. Our radius is 4. Plug in your 4 for the radius, and there you go. It's 112 pi, and finding the decimal of that would be 351.86, round to the nearest hundredth. So whether this thing would be a right, even if it was a right cylinder, kind of like that, going straight up and down, or shift it over to the same, it's going to have the same volume. For the sake of this video, let me just skip over this. This part really doesn't help that much. It's you got the basics down. And let me also skip over, and don't worry about this one. Let me explain the concept to you. If you wanted to find the volume of just the outside here, in other words, you want this triangular prism, you want the volume of the triangular prism, but with this plug taken out. The way you would do that is find the volume of the triangular prism and then subtract the volume of the plug. This plug here would be, or this shaft here, looks like it's it is a square prism. So you'd find the area, the area of the square, and then multiply it times the height, and that volume you would subtract from the volume of your triangular prism. Okay, but in your notes, all that you have is just this one problem here. So this is a triangular prism that's shifted to the side. That's fine, no big deal. So please write out your formula, because it's a prism. It has two bases. Therefore, it's the area of the base times the height. And what is the shape of this base? It is a triangle. The area of a triangle is 1/2 base times height. We're talking the length here of this triangle, and since this is a right triangle, therefore this is your base and this can be your height. Have fun. We'll see you in class. Bye-bye.